In our everyday life, we need metals, and we're kind of taking them for given. We don't notice how many everyday objects we interact with that made of or contain metals, or need metals in order to be fabricated. These metals are coming from the minerals naturally occurring underground. An economic concentration of mineral of interest is called ore. The mineral of interest is not the only mineral present in the deposit. There are others. Some are also economically interesting, some interest us less. Therefore, after the ore has been brought to the surface, crushed and ground, the mixture of different minerals has to be sorted. This is where mineral processing takes place. In function of specific properties of mineral, we adapt the techniques that we may apply to separate it from others. Here I have a sample of magnetite. This is a mineral that is processed to extract iron, and the main contrast property of magnetite is hidden in its name. It's magnetic. I therefore may use magnetic separation to pull the magnetite away from other minerals and concentrate it in a separate stream. Other minerals, let's say chalcopyrite, it's the golden speckles in the stone. Chalcopyrite is iron sulfides used to produce copper. So it can be mixed with certain kind of chemicals called surfactants, and mixing finely ground chalcopyrite particles with right surfactant makes it hydrophobic, giving it an ability to stick to the air bubbles. Its property used in the process called flotation, where mineral mixture is immersed in water mixed with chemicals and air is dispersed into it. Only the hydrophobic particles can attach to bubbles and raise to the surface, forming a foam rich in separated minerals, in our example, chalcopyrite. So the task of mineral processing engineer is to study all the minerals present in the ore, their size distribution, their properties, and design what's called a flow sheet, a schema of subsequent operations that allows to retrieve each interesting mineral in function of their specific properties. Once the minerals are separated into their respective concentrates, they have to be transformed into pure metals. To put it simply, how do I go from this to this? What I have here is a piece of electrodeposited copper. It, in fact, is a good friend of mine, researcher from here. She deposited herself. I think it is just a beautiful example. There are two major paths that we can take in order to produce metal from mineral. First of all, we can heat it heat the minerals until they transform into liquid metal, and we can do that in a furnace. That way is called pyrometallurgy. And we could also apply what's called hydrometallurgy, which would imply dissolving the minerals with the help of an acid and then concentrating and purifying the solution to finally recover metals from it. It's usually considered that hydrometallurgy is a cleaner path to create metal. It's also more precise.
When doing exploration, of course, you are searching for the minerals which are hosting elements of interest. We need absolutely primary resources because the recycling is insufficient. And when we are looking to the rocks, if we are lucky that we find, for instance, zinc ore, you find minerals, and these minerals contain not only the main metal, but also accompanying metals, such as trace elements, which could be germanium, indium, cadmium. So it's a big challenge for the future is to exploit everything. In general, in the past, most mining companies were exploiting only one metal. And the challenge for the future is to not leave in the residues a lot of interesting metals. This is typically what we will have by exploiting granites. For instance, this granite is a lithium-rich granite. It contains a lot of mica. Micas are these fine particles, very brilliant, you find in the sands or in the river, but because they resist to erosion. And in the granite you find such micas, and these micas could contain up to 2% lithium oxide. If you exploit the granite for lithium, you can separate the micas, but in fact all the other metals could be also exploited from the other minerals. For instance, you have rubidium, you have cesium, you could have some oxides from niobium and tantalum, and this is typically what is prepared for the exploitation of these grants. So, of course, you are exploiting the micas, the lithium-rich mineral, but you can also use feldspar for ceramics, you can use quartz for glass, and rubidium for other purposes. So this is a very big challenge, is to exploit everything and not leave any residue. So yes, it's quite important to think from the beginning of the exploration to the byproduct. The reason why is that generally the mine companies are trying to exploit with confidence the main ore, and generally they are a little bit afraid of exploiting other metals because they are not sure to get clients and to make money for this. And of course it costs a lot to have other processes to exploit the trace element. But this is important because if we leave all these trace elements which are very useful for the industry, then we will have to exploit specific ores for this. This is generally not the case. Generally we have only a few milligrams per kilo of these metals. So there cannot be other exploitation than as byproduct. So they are very useful for industry because, for instance, germanium is absolutely necessary for optical fibers. And germanium is only in traces in these zinc ores, zinc sulfides. This is the same for gallium. Gallium is very useful for electronics, and gallium has a trace in the aluminum ores necessary for bauxite, for the aluminum industry. So in all these cases, we need to know what are the amounts of metals in these ores, and then to prepare sufficient processing to extract and not to lose these metals. There are many cases like this. This is the case of indium and in the tin ores or in the sphalerite. There are also scandium, for instance, in the nickel ores. So all these metals could be of a great advantage to extract for the benefits for specialized industries. Speaking of byproducts, cobalt is a good example, for instance. In New Caledonia, in lateritic ores exploited for nickel, there is a ratio of 1 per 10 of cobalt. So you have 10 less cobalt amount, but you have cobalt. But it is almost not exploited because you need hydrometallurgy to exploit it. And this is the same in Philippines or in Indonesia. So all these ores could be a good alternative to the cobalt, which is frequently discussed in provenance of Congo. Congo has 70% of the reserves, the world reserves, but in fact you can exploit cobalt from other sources, especially the lateritic ores exploited at the moment, mostly for nickel.
If we speak of metal coherence, of course, to achieve higher resource efficiency, these metals have to be extracted as byproducts. But it is easier said than done. Extraction of these metals has to be economically justified. There has to be an application for these metals, a buyer, a consumer. It has to be proportional to the demand, otherwise they'll be simply stockpiled somewhere rusting. If such consumer exists, everything is great. We adjust the flow sheet, install extra equipment, produce metal and sell it. But what to do if the metal is present and theoretically extractable, but there is no demand at the moment? The decision has to be taken individually for each case, of course. Is there one of the processing residue streams that is enriched in a specific material that can be stored in a separate location? Would it be smarter to use the material in construction locally and so on. In case valorization of these materials is not possible, it's always important to keep strict track of materials that are stored in residues, not only for safety reasons, but also to allow their reprocessing later when it becomes interesting.
Copper is a concern because the electrification of China consumes more than 50% of the whole copper produced in the world. And it will continue as other countries meet the same kind of emergence of the electrification. We will have an increase in the demand in the next years. So, for instance, Goldman Sachs have previewed that probably the price of copper will increase by a factor of 3 to 4, from $4 to maybe $15 the kilo. The main concern about copper is the grade. The grade has decreased a lot with time, and we have to consider now how to exploit it at very low grade, and we don't know if there are some boundaries in the grades which cannot be reached or overpassed. So the challenge is, in the future, is to produce in a rentable way the copper with new techniques. So that means a field of invention or new theories about the way to extract the copper. And if we extract copper at low levels, that means we can extract also all the accompanying metals in the same ores. Of course, we need copper for electrification, but also we need copper for transmission of electricity in electric cars. In electric cars, we have 4 more amount of copper than in normal cars. The demand will still increase a lot in the next future.
I believe that a lot of jobs in the raw materials sector are very interesting, whether you work in academia or industry. There's a huge potential for innovation, discovery, and improvements to create greener, more efficient processes. And I believe that the younger generation, with their open mind, curiosity, and creativity, can really make a positive impact. And in addition, in Europe, as we move towards raw material independence, there will be more and more jobs available, so this is always nice.
The new jobs are at the interface between a lot of disciplines. You have interface between geology and very new techniques of explorations, using drones, using new spectroscopic techniques. You have a lot of work to do with local population to inform, so there are also new jobs about the way to convince people, but also to explain what are the main trends in the exploitation and the processing. And also there are a lot of jobs at the frontier with economics, because to exploit something in our economic system needs to be aware about all the economic constraints, about the cost of processing, the cost of disseminating the different metals in the society, and this needs integrated studies. So that means that there are new types of jobs which are certainly of very great interest in the future.